We continue Managerial Economics 17, and we continue with econometrics. So let me review very quickly, probably within hopefully 5 minutes of what we did last time. Number one, we did parameters. And we were trying to get the estimates of those parameters. In other words, a parameter will have a true value, which is the actual value that holds in the real world, but is to us unobservable, unknowable, and therefore the best we're trying to do is to get an estimate, a proxy. So true value. The true value related to the concept of a population, the complete population, the full population, which is the set of all possible observations that one can possibly have about a particular topic, subject, area, or whatnot. Okay? And the estimate was basically based on a sample. So a sample represents a subset from the full population. The fundamental reason for using a sample instead of population is cost. It is extremely costly and extremely time-consuming in some circumstances to actually have the full population. Try to think of counting the full population in China. 1.5 billion people going to every single village, asking them the same question over and over and over again. It can take you 10 years to do that. So essentially, cost becomes in many cases prohibitive. That's what we call in economics. Prohibitive cost is a cost which is extremely high to the point of making it, from a business point of view, impossible to do. Even though physically it could be done, it makes no sense to do this whole thing for the Chinese population in 15 years. So we had a regression. And regression is associated with trying to find a relationship between past values. And from regression, you have a regression analysis, which is the statistical methodology used in finding certain type of statistical relationships. And from the regression analysis, you also get a regression equation. And this is just a mathematical function which expresses a particular relationship between the variables. Then we had variables, and the variables were that, just leave it on the table. The variables were independent, and dependent. And the independent stand or sit on the right-hand side of the equation, and the dependent is on the left-hand side of the equation. And if the equation itself could be linear, or let's try this, versus non-linear. Linear versus non-linear. Linear simply means that equation type is y equals a plus bx. And if it is linear, parameter a is the slope parameter, and B, no, A is intercept.
Yes.
You guys sleeping? I'm sleeping.
All I studied was wrong.
Yeah. Intercept. Intercept. And then B is the slope parameter. Okay, so let's see what else we have. Nonlinear is sometimes called curvilinear. Okay. Let's see what next we have. Okay, then we have random error, and sometimes it is called random term. It captures the effects of other variables which do have an effect, but we have not included in the equation for some reason. Okay? Some of these is we don't know they exist. Others are not practical to handle. For whatever the reason, we may possibly have missed some variables, important variables, and these important variables will be captured by the random term. And also, there is in nature and in real life pure chance, pure randomness. That random term will capture that randomness. In other words, when we are working in engineering and physics and science, usually you get no random error whatsoever. The measurements comply with the laws of physics and with the laws of mechanics. There will be error there, and the error will be associated with measurement of the different gauges. In other words, I have a temperature gauge and it says 17.33, but it's actually 17.34 because the tool itself was not measuring properly. Well, in economics and social science, the random error is introduced by humans. Sometimes a human will come a minute late, sometimes a human will make a mistake, intercept with slope, So sometimes humans have different behavior which has certain random element in it. So once you get one human with his little randomness and you aggregate it across the whole market, a whole nation, the error can swing one way or a different way. So errors do exist. Okay? This is sometimes we call it the unexplained part of the equation. In other words, when you have y equals a plus bx plus the error term e, this a plus bx is called the explained. Explained because based on the value of x and the two parameters, we explain that part in e. And this remains as the unexplained. Alright? Let's see what else we have further on. I already explained last time the two fundamental types of data. One is cross-section. You observe the, let's say, interest rate across different countries. Belgium, Russia, Japan, Germany. Or time series, which you observe one particular variable over time. Interest rates in 96, in 97, 98, 99. And when you merge the two, cross-section and time series, you get panel data. For example, unemployment data for 20 years for the 52 different US states or European countries. Okay, so out of this population and sample, you get population regression line. You get a population regression line, which is the true, genuine regression line. And you also get a sample regression line, because the sample will not always be perfectly representative. So whenever you pick randomly 20 or 100 observations as a sample out of 1 million observations, of course these 20 will not quite perfectly represent the whole. So regression line is essentially coming out of linear regression. So when you have a linear regression, the line of this, in this particular case we call it the explained part, represents the regression line. Okay, so what is next? Next is methods or methodology. So it looks like now I'm entering or beginning stuff which I did not cover last time, right? And the most popular method in estimating regressions is known as least squares. So apparently this will need some explanation. So what is least squares? How do we want to draw the line? So here is our, and we kind of do them like this, and we have a regression line, and what we want to do is get this little distance over here. That's, we call this the first error term, or the error term of the first observation. This is like this E1. Then this represents E2. Then this represents E3. Then this represents E4. Okay? This represents E5. E6, right? Is good enough? So, one way that you can do the regression line is, of course, these errors somehow, in some mathematical sense, must be at a minimum. So, one sense you can say that E1, which is with a modulus, plus E2 with a modulus, plus E3 with a modulus, plus dot 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 plus EK with a modulus, and we will try to minimize this function. In other words, what we will try to do is to minimize the distances of the errors. In other words, we'll minimize the total. We call it sum of errors. The sum of errors is what we try to minimize. Now, it turns out that instead of minimizing the distances of these errors from purely mathematical point of view, and also from purely statistical point of view, and finally sometimes from real world point of view, actually we don't want to minimize the sum of the distances. Instead, we want to minimize a different value. And this is E1 squared. That's the first term, but squared. Then E2 squared plus dot 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 plus EK squared. And we may want to take the minimum of this value. Alright? In other words, what you have to do is get a particular mathematical function. It could be a linear function, and of course of the absolute value of each. It could be of a quadratic function. It could be, let's say, of a different function. E1 to the power 4. E2 to the power 4. Plus dot dot dot. Plus, again, EK to the power 4. And you want to minimize this function. So, in the case is F1, there's F2, there's F3, and of course you can provide an infinite number of functions. Well, again, from purely mathematical and statistical point of view, it turns out that the best in some other senses is actually to use this particular function. And this particular function is a function of the squares. A function of the squares. So this means that E1, you get the square of E1. E2, you get the square of E2. So this is oftentimes known as sum of squares. Sum, as in adding the first one to the second one to the third one of squares. Sum of squares. Alright? And squares as in the error to the power of 2. Alright? Is that clear? So, it turns out that this is the best of the best of the best for really good statistical reasons, which usually go in depth in statistical analysis, mathematical statistical courses, which show, prove, and explain why this is the best of all other forms and functions. So this is sum of squares, and you want to take, of course, given the e's, because each of these is the square of it is a positive number, the minimum possible is 0. And if the minimum possible is 0, then when you sum up numbers and each of them is at least non-negative, then the sum will be at least non-negative. Then you know for sure that the minimum certainly exists whenever you have finite number of observations. So I have 5 or 50, the minimum always exists. And this minimum, in English, it becomes translated as the least. The least standing for the lowest possible value of the sum of squares. So the least sum of squares becomes shortened for least squares. So when we say least squares in statistics, we always mean this particular one. Well, what other reason we have statistically to use this function instead of this function? And the answer is for large errors or large deviations, you provide for a large penalty. In other words, when you have a small error like 0.1, you raise it or square it, you get to the power, get 0.01. So, for the very small errors, you provide little or no penalty. But suppose that the error was 10, then the square becomes 100. In other words, this is like what we call sometimes a penalty function. And usually the idea is that, well, when the deviation is tiny or small, then it's no big deal. We kind of like ignore it altogether. What we really care about is the huge, big deviations. And for these, we actually want to provide a large penalty. Well, how would this work, for example? Now, let's try to add one more point on the chart. And that one point is here. So that point is there. We redraw the regression. When I redraw the regression, what you will notice is that the new regression will be practically identical with the old. In other words, it will be the same. Most likely, if we have 15 observations, there is 16 there, the new line will be practically the same. I mean, we won't be able to read the blue from the red. Now, if I put only, instead, one point far out, this point here, and now I recompute, guess what? This huge penalty will actually redraw the line, and the new regression line will be like this. In other words, once you put one large deviation, it starts to attract the regression line. Remember, this here is the regression line. It begins to attract the regression line. In other words, large deviations tend to shift the regression line a lot. In other words, they affect the estimates of the parameters A and B significantly. If the deviation is small, A and B is practically not affected. Alright? The idea is to avoid large mistakes. So, one way that this could be interpreted, the error could actually be interpreted as a business mistake. This is the business interpretation is a business mistake. And the business mistake results typically in business losses, corporate losses. So, what the idea here is that actually what you want to do is you want to reassure yourself of avoiding large business losses. Because business losses could be so large as to potentially bankrupt the company or the business. Alright? Is this now making it clear? Now, if you instead were not penalizing large errors through their squares, but were using this function, then when you redraw this line, so this is if you use squares. If you recompute with squares. But if you recompute it instead of the squares, but you recompute with, we call these absolute values, again, the new line will be very, very close to the original line. In other words, the regression is extremely sensitive to large deviations, and it is sensitive because we intentionally designed it so, because we wanted it to be that way in the first place. Because the business interpretation is we want to avoid large mistakes that could potentially result in large losses. Is this clear? It makes sense? Do we move on? Questions? No? Okay.
The squares, this is what I know from previous studies that, is this the MSE?
MSE, minimum squared, yes, estimate, yes. Yes, this represents the MSE.
And the other one is the MAD, MAD?
Yeah, I don't know for the other one because it's been like...
But usually managers use the MSE more.
Yes, of course. Yes, of course. So the other one is, so this is mean squared errors. The other one mean absolute error. Okay, would make sense. I've rarely ever seen this one. Okay, I mean this one. Okay, let's try to do this. MSE is the same as F2. All right, F2 is MSE, mean squared errors. Okay, well, what does it mean? It means that this is the error and this is a squared error. So we call this a squared error, okay? And then this is the squared error, okay? And the mean means that you take the average of these squared errors. Of course, you're going to take an average. Of course, you're going to take the mean. You have 50 observations. The squares of those errors will be 1. And if you take 500 observations, the square will be 10 times bigger. But you want to take the average of the errors, the average of the squared errors, which you actually want to minimize, okay? So this MAE will logically represent F1. And essentially, yes, what we want to do in business is this piece over here, because it just makes more sense from a business point of view.
There is also the MSPE, the percentage of the...
Yes, there will be a percentage and other stuff, so you had these in your statistics course, right? Correct?
Yes.
Already, okay, well, good for you. Let's see now what we have. Alright, so essentially, the method, so now I'm doing a little trick, the method which uses the least squares as a statistical technique is called the method of least squares, or sometimes the least squares method, alright? And is the most popular one. There are 2 other methods which are used in statistics, and for most practical applications, it is actually part of statistical theory, to prove mathematically that the three fundamental methods, the other one is method of maximum likelihood. Have you studied maximum likelihood? Probably not. And another method of moments, the three fundamental methods, method of moments, maximum likelihood, and least squares for most applications, depending on some other statistical conditions which are typically satisfied in the real world. The three methods are fundamentally identical. So whichever method you choose does not matter. The result for the same function the three methods will compute identical parameters, will produce identical results. Okay, so what's next? What is next is I'll reuse this one over here. I use this one over here. So what we have is, again, our regression, and this is the regression line, and suppose you have this particular observation. Well, this observation is represented by, if this is, let's say, x1, the first observation, is represented by this point here. Okay? So this, the first one, the blue one, we actually call the actual value. This is the actual value, or sometimes we call the observed value. This here represents the error, so for the first observation will be error number 1, for observation 4 will be error number 4, and this here is called fitted value. So what the fitted value does is essentially tells us what is the value of the function if there was no error. Well, what does it mean to have no error? Well, one of the simplest interpretation is if it sits on the regression line. If it lies on the regression line. Well, why do we call it fitted value? Well, because it represents the best fit. In other words, for all of these, the sum of squares, the concept is that if you minimize the value, the regression line represents what is known in statistics as a best fit. Best fit simply means the line, and now I'm using a tautology, which fits best to the data. In other words, this is the line which is somehow closest to all observations. So this is what fit means. Fit means it fits the data. It is close to the data. And best, again, is represented by the sense of a minimum. The minimum sum of squares. And of course, we get it by minimizing this particular function. We minimize this function. So this is called fitted value, but is also known equivalently, and everyone's using these two terms interchangeably, as forecasted value. Forecasted value. Forecasted, and sometimes they just say forecast value. So both are actually used. In English, you have cast, cast, cast. So technically it should be forecast value. It should not be used forecasted. Okay? Forecast value. So what does forecast value mean? Well, it means very simple. If we are trying to make xk plus 1, in our case from last lecture, suppose this is the quantity of this is the quantity of the fertilizer that we use. If this is the quantity of the fertilizer that we use, so here in our example we have fertilizer, and here we have yield or output. Well, what is the forecast value? In other words, what is our best forecast about the, in this particular case we say expected yield. Expected yield. Well, it will be exactly the value of y which sits on the line and corresponds to this k1. So, again, because forecast in English is the same as predicted value, this is our best, we call it prediction, our best prediction. So sometimes they call it predicted value. Again, the idea of what we do now is not to learn statistics, it's actually to learn the interpretation of statistics, the meaning, and to learn the fundamental concepts. The idea here, all I'm repeating, is you will have a professional statistician, right? And he will give you, and he'll say, well, the predicted value of whatever, or our forecast, or best forecast is, well, he means these same things at the same time. In other words, when you read a statistical report, the objective is for you to understand different words, what they mean. And sometimes these can be confusing unless you know that they all mean the same thing. So, in this particular case, the predicted value will be whatever this value is going to be k plus 1. Alright, is that clear? Makes sense? Is it logical? Have you studied this already?
Some of it, not all.
Some of it, not all of it. Okay, let's see now. So, from last time, usually you will have, in order to evaluate a particular parameter or to estimate a particular parameter, you will use a function, and this function is called an estimator. So, the estimator is actually a, my mistake, function. And this is a function which is based entirely on the observations on the axis, x1, x2, x3, and y1, y2, y3. And when you substitute in the function the observations, you will get the estimate. And the estimate is actually a value. And sometimes the estimate is actually called estimated value. So the estimated value. So the estimate represents a value. It is a number. We call it scalar. Scalar. Alright? And the estimator is actually a function. Alright? So when you plug in the numbers in the estimator, you get the estimate. Alright? Fairly straightforward. Okay. So, next thing is, and I think we're moving hypothesis. We're moving, I would think, yes, to the next section, like 4.3. Here's one other thing. Here's one other thing. Fitted or predicted value. And this E1, the error term, for the estimated value, we call in statistics a residual. So, the residual is actually the epsilon. Remember, we were using Latin letters and we were using Greek letters. The Latin letters represented the population. The Greek values represented based on the estimates and on the sample. So, whenever you compute it based on the sample, you call the value a residual. So, the residual represents the concept of the random error and represents the concept of the random term, but the residual is after you have evaluated, and the residual is based on the estimate, the estimated values, and is based on estimate, not on the true population. And they like to just call it residuals, alright? So, testing and hypothesis. So, hypothesis, testing, All right, let's see now what we are getting all together. So first of all, what does it mean to test? To test, and in this particular case we call it statistical test. Statistical test is to provide some sort of a procedure by which you can actually verify whether a particular statement is statistically true or statistically false. You guys know what statistics actually mean in general?
Statistics is the study itself. Statistics is the subject or the study itself, but statistic is the adjective.
Correct, but the statistical, what does it come? What does it mean? It means, or it's coming out of the word random and randomness. So statistics essentially is the subject or science of randomness, okay? And if you have a whole process which is random, we call it stochastics. Stochastics is the subject of random processes. Alright? For example, interest rates floating over time. Could be floating as a Brownian motion or some other, like a random walk, some other stochastic process. So, statistical essentially means, the statistical test will essentially mean that based on the randomness, something may be true or something may not be true. And based on the observation, it will provide us a particular level of confidence. Whether our conclusion is fundamentally true or not. Of course, the confidence is not 100% because, number one, we assume we don't really know the truth, and we assume we don't really know if there is a genuine effect. It may be that based on the different quantities of fertilizer, the higher the quantity was, the higher yield we were getting, but it could be based on purely random circumstances. Like every time we had more fertilizer, actually there was more sun. And if there was more sun, then you got a higher crop. Or whenever we used more fertilizer, there's been actually more rain. And rain contributed to the crop. In other words, it could have been possibly two other factors. Well, if we have only two observations, very difficult to tell. Was it due to rain? Was it due to sun? Was it due to fertilizer? If we have 5 observations, it is still relatively difficult. And of course, all people will tell you that in 5 years you can't really figure it out. But if you have 500 observations or 5,000 observations, maybe over 50 years, maybe over 100 different locations. In other words, you got panel data, 100 different observations, places, each with 50 observations. You have 5,000 observations. Then you could be relatively confident that if you establish the relationship, and if it's there, that most likely the relationship actually exists. So I use the next concept of confidence. Confidence. Or let's take a pause for me to wipe out. It's party like